All right, as we get started, let's go ahead and turn to practice exercise number 19. Practice exercise number 19, the last several practice exercises. We've been working with fractions, adding and subtracting class. You got to have a common denominator. Multiplying, remember, you don't. You cancel stuff. Dividing is where we're at now. But do we really divide fractions, class?
No.
What do we do? Which means we flip the fraction that is after the division sign, right? The one after the division sign gets flipped, and then we multiply, we do the canceling. Basically, it becomes like exercise 18, only not as long. Exercise 19, go ahead and begin. You want to work on extra paper? Certainly can. Exercise 19. Remember to write answers as mixed numbers, not improper fractions. one more minute to be working on this. All right, put your pencils down if you would, please. And if you would, go and take out a pen. Put your pencils away. And if you would, go and take out a pen. See if Brecken and Josh, if you two can exchange, and then you two, sets of three, just swap amongst yourself, pass it behind, back person, get it up to the front. And we'll do it that way. So pencils off your desks, pens out, and exchange. Sign your name in pen if you would, next to where it says exercise 20. Sign your name in pen next to where it says exercise 20, there at the bottom of exercise 19. And these will be 8 points each. 8 points each. Top row going across, your answers are 2/3, 1 1/7, 54, 1/20. Again, 2/3, 1 1/7, 54, 1/20. Next row going across, 3/80, 24, 64 75ths, 1 5/22. Again, 3/80, 24, 64 75ths, and 1 5/22. Bottom row going across, 4/15, 7 128ths, 20 5/6, 7/10. Again, 4/15, 7 128ths, 20 5/6, 7/10. All right, figure the score to the best of your ability. They are 8 points each, so total number wrong times 8. Subtract from 100. Put the score next to where it says exercise 19 and circle it, if you would, please. Write the score next to where it says exercise 19 and circle it. Yes, sir. Question?
8 points each.
8 points each. Yes, sir. All right.
So,
4 free points were taken. All right. All right, return to the owner if you would, please. Go ahead and return back to the owner. And let's see, Michael. Michael, you were first, no 100. Who is second? Noah? 100? No. Third, Brandon, but no. Fourth, Lana? No. We'll take questions in just a minute. Fifth, no. Sixth? All right.
Oh, really?
Yes, you said you got it?
Yeah.
All right, so you were the first 100. All right, there we go. Now let's take some questions over these. Lana, yes, ma'am.
Like number 1.
The very first one, we had a 3/5. And it says divided, right, Lana? We can't divide, so we're going to multiply by the reciprocal, 10/9. And then we can cancel the 3 with the 9 to get a 1 and 3. 5 and 10 to get 1 and 2, so we get 2/3. What did you have?
Oh, I had 2 9s.
Okay, all right. Good. Any other questions? Any of these? Yes, sir.
what was the second one?
Very second. 8/7, which became 1 1/7. So we had a 6/7, and it says divided by 3/4. We say times 4/3. Cancel to get a 1 and 2. So there's your 8/7, which is 1 1/7.
No, I accidentally saw.
Oh, okay. Other questions? Question? Going once. Going twice. All right, pass those forward if you would, please. And take your homework handout out. Go and take your homework handout out. Get a picture that looks something like what's on the board. An isosceles triangle ABC, but the base was extended out to points D and E, equal amounts. Take the homework handout out. Hold it up if you would, please. Just kind of leave it up so that I can see that it is complete. So hold it up and leave it up so that I can see that it is completed. Excellent. All right, let's go and take a look at this. Obviously, without doing any thinking at all, we should be able to write our first statement. And so, let's see. Somebody without thinking. Michael! Just kidding. Michael, what's our first statement?
Isosceles triangle ABC with AC equal to BC. AB extended through A to B and through B to E so that AB is equal to BE.
All right, I'm going to cheat just a little for sake of time. And while it's good to know that AB is extended, so that tells us this is indeed a straight line, not just appearing to be. I'm not going to copy it down just for sake of time, but you should have, and on a quiz or test you certainly would. All right, and of course your first reason you wrote?
Angle A equals angle B.
Your first reason you wrote?
Given.
Given, very good. All right. Number 2. I gave you the reason for number 2, but you shouldn't have needed it, because every time we start a proof, the first thing we're looking for, class, is Clang. And there is one Clang statement. What is our Clang statement here? Noah? Well, kind of the part that follows it is what the two equal sides are. But yeah, isosceles, two equal sides. Because we said that if we had a triangle class and two sides are equal, Clang. Angles are equal, right? The opposite angles are equal. So in this triangle, ABC, if these two sides are equal, what's the Clang response to these two sides being equal, Noah? This angle with little a and this angle with little b are equal. Why did I not use numbers? I don't know. All right, so how many have little a, angle little a equals angle little b? All right, and the reason was already written there for you. Angles, opposite, equal sides. What are the next three words, class? In a triangle, in an isosceles triangle. It's fine. I doesn't even have to say isosceles necessarily, but I put it on there apparently. In an isosceles triangle are equal. So it's true in triangles, or in a single triangle, that angles opposite equal sides are equal. And then number 3, I said that angle 1 plus angle A equals a straight angle. I even gave you the reason. That seems cheap. And angle 2 plus angle B equals a straight angle. Go ahead and read the reason for us, Josh.
The sum of all the angles about a point on one side of a straight line equals a straight angle.
Good. The sum of all the angles about a point on one side of a straight line equals a straight angle. Aren't you thankful for shorthand? And then so I said next that, well, if this is a straight angle and this is a straight angle, class, we know what about straight angles? All straight angles are equal. So number 4, what was the statement we made next? Reckon?
Angle 1 plus angle A equals angle 2 plus angle B.
Good. Because, as we just said, class, and so kind of what we did, it's not quite the whole is equal to the sum of all of its parts, but it's kind of a similar idea that all together this equals the straight angle, all together this equals a straight angle. And then because the straight angles were equal, I was able to substitute the parts in for the equal straight angles. It's kind of like a substitution, though not exactly. And then the kicker was number 5. I said if equals are subtracted from equals, the remainders are equal. I'll just put the word subtraction up here, or subtraction axiom, right? But what subtraction actually takes place here, Dylan?
Subtract angle A and angle B.
Right, we'd said that A and B were equal, so now if I subtract the A and B away, it leaves us with what statement here for number 5?
Angle 1 equals angle 2.
And that was the first thing I was trying to prove. How many had angle 1 equals angle 2 there in number 5? Now again, I didn't make you come up with the progression here, but does it make sense? We say what the parts add up to. Since they add up to things that are the same, I can subset them equal to each other. Quantities equal to the same quantity are equal. You could also say all straight angles are equal, which is what I did. And then we can subtract away the parts we already know to be equal to leave us with parts that are. Does that make sense? So then number 6, we got one more thing to prove. We haven't done any analysis yet, mainly because the proof was kind of filled out for us. I need to prove that two triangles are congruent, DAC and EBC. Of course, we were given these two extensions, AD and BE, were equal. We were given these two sides equal, and we just proved that angle 1 equaled angle 2. So class, with these two triangles, we already have side angle side. So yeah, number 6, you should have stated that triangle DAC is congruent to triangle EBK, and the reason side angle side. Again, I know you didn't have to come up with very much of this proof on your own, but how many did nail it? Got everything correct, filled in. All right, questions on it? Questions on it? Going one. Going twice. All right, let's set that aside if you would please. And take out your notebooks. Turn to the theorems corollaries section. Theorems corollaries section of your notebook. Continue to add to our base of knowledge, which adds tools in the toolbox, so to speak, for proving things later. Theorem 4, right there below corollary 3-1 in your notebook. Theorem 4 says this: two triangles are congruent. Two triangles are congruent. Had a notebook malfunction.
Yeah.
Two triangles. You can copy.
Every time I drop it, it falls apart. So.
Try not to drop it. You can copy it down afterwards. So focus on getting it fixed. Just copy it down from a classmate afterward. It's the only theorem we're doing today. Two triangles are congruent if the three sides of one triangle. Two triangles are congruent if the three sides of one triangle are congruent to the three sides of the other. Two triangles are congruent if the three sides of one triangle are equal, respectively, to the three sides of the other. The three sides of one triangle are equal, respectively, to the three sides of the other. Two triangles are congruent if the three sides of one triangle are equal, respectively, to the three sides of the other. And then in parentheses, if you would, after you've written the theorem out, in parentheses put SSS. Capital SSS, side, side, side. This is our side, side, side theorem. Two triangles are congruent if all three sides of one equal all three sides of the other. Now, question, right? What does congruent mean again? Adam, what does it mean for things to be congruent?
Be the same size and shape.
Yeah, same size and shape, coincide throughout. Wouldn't three equal sides kind of already be congruent? Like if I have a couple figures and all the sides are equal, don't they have to be congruent? Think about this. What if I drew, let's just say a square. Okay, let's go away from the world of triangles here. And all the sides of the square were exactly this long. Well, what if I drew another thing with four sides this long? Would it have to be congruent? Noah's like, no, why not? Oh, so if I slanted my sides, I could still have all these sides equal to all these sides. So the perimeters, if you will, would be the same, but would they necessarily be congruent, class? No. So just because sides are equal, that doesn't necessarily mean they would coincide throughout, nor even be the same shape, because the angles wouldn't necessarily line up. Does that make sense? Remember, we have to have all the sides equal and all the angles equal in congruency. So no, this isn't a self-proved theorem. We are going to need a little deductive reasoning. If you would, turn to the proofs of theorems corollaries now. Proofs of theorems corollaries. And at the top of a new sheet of paper, put theorem 4, side, side, side. Theorem 4, side, side, side. Theorem 4, side, side, side. Down below it, if you would, draw a couple triangles that to the best of your ability appear to be congruent. So draw a couple of triangles that to the best of your ability appear to be congruent. They don't have to be perfect because we're not trusting our eyes anyway, but they should look pretty close. Best you can. Just don't waste time on it. All right, let's call the one triangle ABC, and let's call the other triangle XYZ. we are given triangle ABC and triangle XYZ with, remember the conditions of the theorem. The triangles are going to be congruent if, class, the three sides are equal to the other three sides, right? So let's say that, for instance, AC and XZ are equal. Let's say that BC and YZ are equal. And let's say that AB and XY are equal. So given triangle ABC and triangle XYZ with AC equal to XZ, BC equal to YZ, and AB equal to XY. And inevitably I need to move the lectern, don't I?
I can see it.
Oh, I don't need to move the lectern. As long as Lana can see. I'm picking on you. All right, we want to prove that triangle ABC is congruent to triangle XYZ. Now, of course, one thought in getting congruent triangles, right, would be to show that they coincide throughout. I don't like to do that. Especially now when there's a couple easier ways. And there are a couple easier ways to prove triangles congruent that we've used quite a bit lately, class. Yeah, side angle side and angle side angle. Like angle, we already know those only apply to right triangles, so we'll pass on that. Which of these two ways, just to you think, I think this would be the best way? And why do you think it would be the best way? Should we try for side or angle side angle, and why? Lana?
Maybe side angle side.
Why?
Because it's always the why.
Always, in this class especially, it's always the why.
Because there's.
Or is it just like, I like that one better? Brandon, do you agree with Lana or disagree with Lana?
I agree.
So you agree with Lana. Do you have a why for your agreement with Lana? Because if you're agreeing with Lana, you really ought to know why. I'm just picking on Lana. Go ahead.
We already have two sides equal.
Yeah, I mean, this uses two equal sides. This only uses one. What do I have a whole bunch of, class? Equal sides. So lazy me is going to find the one that uses as many of those sides as possible. And if I use side angle side, I only got to get one pair of angles equal. If I go with angle side angle, I got to get more angles equal. I don't want to do that. I'm lazy. So let's go with the side angle side. So bottom line, you realize if these two angles are equal, congruent triangles, or these two angles equal, congruent triangles, or these two angles equal, congruent triangles. Really doesn't matter. As long as somewhere, somehow, some way, I get a pair of corresponding angles equal, I'll have my side angle side. Thoughts on how to get the angles equal? Michael?
AC and XZ are equal, so their opposite angles are also equal.
Oh, careful. Angles opposite equal sides in a triangle, in one single triangle. Are these two sides in the same triangle? So can we get their opposite angle? Oh. Rats. Mice. Gerbils. Other assorted rodents. All right, anyway, sorry. Other thoughts? I mean, this line is the same length as that one, and this line is the same length as that one, so don't these two angles have to be equal, like, because the lines are the same length? No, remember, equal length lines doesn't make angles equal to each other, so that's not it. Noah?
Can you get it with just one triangle first, since the sides are equal?
Well, in just this one triangle first, which sides are equal?
AC and CD.
They're equal to each other? I mean, they're not, it doesn't say they're equal. It says BC is equal to YZ and AC is equal to XZ. Now, I guess if these two lines were equal, then those would be, and then some equal line. Yes, sir.
Can we say that? Oh, wait, no, we can't.
Yes, sir.
Can we skip to the part where we use side?
Well, you can't use side to prove side. Where it's like, I'm going to prove that I am the smartest man in the world. So first of all, Adam, I'm the smartest man in the world, and I think that proves that I'm the smartest man in the world. I'm going to prove that all three sides equal all three sides makes them congruent. You know how I'm going to prove it? Because all the sides are equal, and therefore they're congruent. Wait a second. Circular logic. What?
Do we need to draw like an auxiliary line?
Okay, his suggestion was we may need an auxiliary line here. And that's kind of my thought as well. My other thought is y'all keep trying to say in a triangle. And these two triangles are not one, but what if I kind of not put them on top of each other? Because remember, without knowing the angles line up, you really couldn't put these on top of each other. But what if I kind of smushed them next to each other? That's going to be our plan of attack. So, Michael, these two lines are equal, and right now they're in separate triangles. But what if I, picture this, picked this up, flipped it upside down, and put it up under here so it looked kind of like that? And then taking the auxiliary line idea, if we drew a line right here, this line would be here, that line there, and now we have a triangle. Okay? So that's actually what we're going to do. Going into two columns, statements, reasons. If you haven't already, copy down your first statement, your first reason. And this one's got a rather elaborate move through space thing that we're going to have to do. So we are going to take the ideas of, in a triangle, angles opposite equal sides are equal. We're just going to make kind of one triangle out of it. And again, the use of the auxiliary line that was suggested is going to enable that also. So triangle ABC, triangle XYZ with AC equal to XZ, BC equal to YZ, and AB equal to XY. All right, so the wording is a lot of fun here. We're going to place triangle, or actually let's say this way because we're flipping it first, right? Flip triangle ABC and place under triangle XYZ, flip triangle ABC, and place below triangle XYZ so that, here's the fun part, we flipped it, and we're going to place it so that, as we said before, a point can always coincide with another point. So we're going to place it so that A falls on X, and a B falls along XY. So A is going to fall here, B is going to fall somewhere along here, but it's also flipped so that C is down here. Let me use blue to show this. B is somewhere along here. And then you've got the C down here. All right, do y'all follow what we're doing? Sketch that on your papers. Oh, one more thing. We did need to mention C falls opposite line XY from Z. And C falls on the opposite side of XY from Z. It's a lot of finagling. And again, you're not going to have to do this on a proof you come up with yourself. Okay, homework proofs, quiz proofs, test proofs. You're never going to have to do this process of placing and flipping and all that nonsense. What would be my reason, though? We've done this a couple times. So anyone remember what reason we used to justify all this flipping and moving and placing and lining up and nonsense? Yeah, the move through space, right? A geometric figure may be freely moved through space without any change in form or size. I'm going to write move through space. All right, the next thing that we need to observe is since C is down here somewhere on the opposite side of XY from Z, I can then draw CZ, and that's going to be number 3. Draw CZ. Now, when I say draw CZ, you shouldn't be thinking, well, where should I draw it, though? Why shouldn't you wonder where to put it? Because C is a point down here, and Z is a point up there, and how many CZs can you draw? 1, because 2 points determine a straight line. That'll be my reason here. 2 points determine a straight line. All I'm doing is connecting one point to another, and so we've got our line CZ. I'm gonna add this in with CZ. Well, I guess technically I shouldn't, logically, so we'll state this. A is a point coinciding with X. C is a point down here. Z is a point up here. X, or A, CZ forms what shape now, class? A triangle. So X, C, Z is a triangle. How do we know it's a triangle? 3 sides. Definition of a triangle. Geometric figure bounded by 3 straight lines. What about this B though? Remember we said B falls somewhere along here? What doesn't just fall somewhere along there, class? Thoughts?
Falls on one.
Where?
Falls on one.
Why must it fall on Y?
Because A and B is equal to X.
Or XY. Yeah, if the segments are equal, then endpoints can be made to coincide. So then we could state number 5B coincides with Y. Which means B and Y are now the exact same point. Reason, class? Definition of equal line segments. Okay, so X and A are really all 1 point, B and Y are really all 1 point. Well, in that case, B or Y, C, Z are 3 points. Not 4, but 3, correct? And therefore we have 3 straight lines. So therefore, YCZ class is also a triangle. So number 6, we can say that YCZ is a triangle. Again, definition of triangle. Now, why is it important to state that we have a triangle? Well, I want you now up here at Z, call these 2 angles 1 and 2. Down here at C, call these angles 3 and 4. We know that XZ equals A or XC. That was given, right? And if I have 2 equal sides in a triangle, then we know that, what was it again, Michael? You're the one who said it first. Say, pay attention. I've got here a triangle with 2 sides equal.
Opposite equal, angles are equal.
Angles opposite the equal sides in a triangle are equal. So if I never said we had a triangle, right, it's like Lana has done all these terrible, heinous things. Lana is guilty, but we never established that she is Lana. None of that applies to her, right? Well, it's great to say that angles opposite equal sides in a triangle are equal, but if we haven't stated that we have a triangle, makes sense? So, yeah, so we know next, let's see, that would be statement 7. I'm going to come over here since I'm out of room down. Number 7, that angle 1 must equal angle 3, Michael, because
in a triangle, angles are opposite sides are equal.
Equal sides
Yeah.
are equal. In a triangle, angles opposite equal sides are equal. Let me expand the screen just a little bit, make sure we're getting everything there. But on a similar note, Brecken,
Angle 2 equals angle 4.
why?
Because angles opposite equal sides.
You know, what equal sides do we have?
YZ and YC.
YC or BC, right? They're the same point, so YC or BC. Yeah, BC and YZ were equal. So for these 2 sides are equal, so yeah, angle 2 and angle 4 are equal for the same reason. Make that part of statement 7. 1 and 3 are equal, 2 and 4 are equal. So this is great now, right? What did we want? We wanted some angles. Why did we want some equal angles, class? So we could use side angle side. We got some equal angles now, right? Sort of. Sort of. Thoughts? Not any angle in this triangle, right? Angle A does not yet equal angle X. Angle B does not yet equal angle Y. Angle C, which is down here now, does not yet equal angle Z yet. But, Josh, thoughts? Adam, rescue? Because to use side angle side, I either need these two angles equal. They ain't yet. B and Y equal. They ain't yet. And C and Z equal. Okay, Adam?
You could use CPCT.
What does CPCT stand for?
Corresponding parts to congruent triangles are equal.
So if I had congruent triangles, then no parts were equal. Do I have congruent triangles yet?
No.
Oh, can't use that then. What is angle C, class? What is angle C? Angle 3 and 4 put together, right? What is Z, class? 1 and 2 put together. So we've seen this the last couple of days. Go ahead, Brandy, start it anyway. The whole angle Z is going to equal the sum of its parts. The whole angle C is going to equal the sum of its parts. Let's go back to Adam. That's a Z, not a 2. What would we say angle Z equals, Adam?
Angle 1 plus angle 2.
And what would we say angle C equals, Josh?
Angle 3 plus angle 4.
Angle 3 plus angle 4. Because, class, and so since 1 and 3 are equal, and 2 plus 4 are equal, if I were to, add equals to equals, it might say something like this. Take angle 1 and angle 3, which are equal, and add to them, class, angle 2 and angle 4. And what I've done is I've added equals onto equals. And we know that if equals are added to equals, the sums are equal. That's the addition axiom. I'll just say addition, one word, because I'm lazy.
Wow.
And then, because we've said that 1 plus 2 equals 3 plus 4, and I know that 1 plus 2, class, well, that's Z. And angle 3 plus 4, well, class, that's angle C. I can just take the Z and the C and just substitute. So number 10, angle C equals angle Z, or Z equals C, by substitution. And so all of that nonsense, all of that craziness, so I have C and Z equal. And we already knew that AC equaled XZ and that BC equaled YZ. So class, what do I have marked in pink? Side angle side. Number 11, finally, we're done with the proof. The triangles are congruent by side angle side. Whew, a lot of elaborate work just to get those triangles congruent.
Let's just say
No, we can't do that. We can't do that. It's a logical fallacy. But now, moving forward, if I saw a side, 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 I would know that triangles have to be congruent because we just proved they have to be. 3 equal sides, it takes a little finagling, but you can get them congruent by side, side, side. So again, it has just one more tool to the toolbox here. We've already proven side angle side and with it leg leg. We've proved angle side angle and with it leg angle. Now we've proven side side side. We've got to wait on the others a little bit. We've got these down for now at least. Questions on this? Not asking if you could do it on your own. I wouldn't expect you to, but does it make sense? All right, go ahead and go to the class notes section of your notebook. Class notes section of your notebook. And at the top of a new sheet of paper, go and write this statement. Or on the back side of a sheet of paper. Maybe you've got a piece of paper already in there, but the back side is clean. I just want either a whole front or a whole back of the page. I'm going to write this statement down. The line from the vertex of an isosceles triangle the line from the vertex of an isosceles triangle, the line from the vertex of an isosceles triangle to the midpoint of the base, line from the vertex of an isosceles triangle to the midpoint of the base is perpendicular to the base and bisects the vertex angle. To the midpoint of the base is perpendicular to the base and bisects the base. Line from the vertex of an isosceles triangle to the midpoint of the base is perpendicular to the base and bisects the vertex angle. By the way, what do we call a line from a vertex to a midpoint? Not an altitude, that's a perpendicular. Median. A median. So you could say the median from the vertex to the base. Yeah, whatever. All right, so let's go ahead and draw down below that statement an isosceles triangle, or what looks like an isosceles triangle, and call it ABC. Locate to the best of your ability the midpoint of the base. Let's call it M for midpoint. And go ahead and draw that median, CM. Go and draw that median, CM. We're given an isosceles triangle, ABC. Now, since I'm making this the vertex angle, AC and BC have to be the legs, so we'll go ahead and state that AC and BC are equal. And let's say M is the midpoint of AB. M is the midpoint of AB. We want to prove two things. That if you draw that median, that line from vertex to midpoint, it'll be perpendicular to the base. So we want to prove that CM is perpendicular to AB. And we also want to prove it bisects the vertex angle. CM bisects angle C. Once you have that down, two columns, statements, reasons. Well, I'd say it's significant that we have M is not just a point, but class, it is the midpoint. Clang? AM equals BM. Reason? Yeah, definition of a midpoint. Divides a line into two equal segments, so state what the two segments are and say it's because of the midpoint. Blame it on the midpoint. I can't help also noticing that as I draw this line, class, it takes what was a single triangle and turns it into two triangles. We almost always seem to want to get triangles congruent, and after all, isn't this line equal to itself? So, for instance, number 3, we could say by identity. And we just proved that if all 3 sides here equal all 3 sides here, class, congruent triangles. So, I mean, it didn't say in the proof it wanted me to prove congruent triangles, but I just kind of like, we usually need to. So let's say the triangle CAM is congruent to triangle kaboom. Kaboom. Anyway, reason?
Side, side, side.
Side, side, side. Now, here's the bigger question. Now that we finally get to our analysis, does it help me to get these two triangles congruent? How would that help me, for instance, to show that I've got a perpendicular, or to show that I've got a bisector? What about CPCT?
Well, we can say that. If we like label the C
and 2.
Okay, so if I label these 1 and 2,
I would say that angles 1 and 2 are equal.
okay, that's true, right? Angle 1 does equal angle 2 by CPCTE. Somebody else, how does that help me though? Somebody like Brecken. How does it help that 1 and 2 are equal? I mean, they are by CPCTE, but, well, I already have side. I already have congruent triangles. I don't. Dylan?
Well, if the line CM bisects.
We don't know that it bisects. I'm trying to prove that it bisects. Noah? If 1 and 2 are equal, then it must bisect, correct? If 1 and 2 are equal by CPCT, but because they're equal, this has to be the bisector, because what does a bisector do, class? Two equal angles. I have 2 equal angles. That must be the bisector. So therefore, number 6, we can say CM bisects angle C, based on the definition of an angle bisector. Now normally, right, we're given the bisector, we say, clang, 2 equal angles. Weird. Hey, there's 2 equal angles right there. Clang, it must be a bisector. I wouldn't necessarily call that clang, but kind of a reverse clang. If you mispronounce. Anyway, so hey, we actually took care of the second thing we wanted to prove first. That's okay. Need a perpendicular. Gotta have a perpendicular. Oh, so you're over here now. I'm looking over there. I'm like, you know, perpendicular boys over there. Gotta have a perpendicular. Dylan?
Well, the bisects, if CM bisects C, and it goes to the midpoint of AB, they should be perpendicular.
And what?
They should be perpendicular.
Why should it be?
Because in the statement it says that.
Well, we're trying to prove the statement. A couple ways we could go here. The easy way and the hard way. All right, let's do the hard way. Oh, you got an easy way.
AM equals BM.
Yep. We said that.
So therefore, isn't it a midpoint?
It is a midpoint. Yep, right here in the given.
So wait, you have to find out if.
So if we have a midpoint,
find out.
right, and we have a line that goes through the midpoint, it's perpendicular?
No, if it has right angles.
Oh, if it has right angles. Okay, so in other words, if I could show I have right angles, then I got a perpendicular? Yes. Like, I don't know. Yes, if I have right angles, I know I got perpendicular. So let's call these 3 and 4 perpendicular. So if I could get 3 and 4 to be right angles, I'd have a perpendicular, wouldn't I? How can I get right angles? Adam?
You have to prove that 3 and 4 are equal.
Okay, so if I prove that 3 and 4 were, are they equal, class?
No.
We don't know.
Well, I don't know.
Because CPC.
Oh, because CPCTE, right, they are. Angle 3 does equal angle 4. So since these 2 angles are equal, that makes them right angles? Just because angles are equal? No, but they're not just 2 equal angles. They're equal angles that are formed when two straight lines intersect. And they're not just two angles formed when 2 straight lines intersect. They're 2... Because, for instance, here, I have 2 angles that are equal when 2 lines intersect. They're equal adjacent angles, right? These are adjacent angles, and they're equal adjacent angles when 2 straight lines intersect. So by definition, angle 3 and angle 4 are right angles. Definition of right angle. And if we have right angles, class, we do indeed have perpendicular lines. CM is perpendicular to AB. That's the hard way, but it works. Definition of perpendicular
What was the easy one?
lines.
Yeah, 'cause that's
To find the easy way, you're in the class notes section, right? Flip 1 page back again in your class notes. And you should see a statement that says, if the bisector of the if you bisect the vertex angle of an isosceles triangle,